In February 2013, the Pentagon directed the Army to develop a transportable, high-throughput bulk agent destruction system capable of meeting Chemical Weapons Convention destruction standards. These requirements meant that the system had to be designed in modules for relative ease of transport on a common platform and assembly at an operational location. It also needed to be capable of processing a high volume of material compared to other technologies. And it needed to be capable of safely handling chemical agents and precursors stored in non-weaponized containers. Upon determination that no such capability existed in the U.S., key partnerships formed to develop a path forward. Among these partners were the Joint Program Executive Office for Chemical and Biological Defense and the Joint Project Manager for Elimination Provisional, who brought to the table more than 40 years of experience in the destruction of U.S. chemical weapons stockpiles and recovered chemical warfare materiel, the U.S. Army Edgewood Chemical Biological Center, whose rapid prototyping capabilities and field operational experience led the effort to construct a functional prototype, and the Defense Threat Reduction Agency, who partnered in validating requirements and provided funding for the first prototype. The result of these partnerships was the Field Deployable Hydrolysis System, or FDHS, a transportable, high-throughput chemical material neutralization system that combines the best of the nation's lessons learned from decades of experience. The same neutralization technology used in the FDHS was used by the Army to destroy more than 7,000 tons of chemical material in the U.S. since the early 1970s, including 2 stockpiles and several recovered items. The FDHS was created, fabricated, and deployed within a year, an exceptional time frame accomplished through lessons learned from past experience, local fabrication, and the use of existing equipment. The system was transitioned to the Joint Project Manager for Elimination Provisional in June 2013 for advanced development. The FDHS was initially envisioned as a land-based system. In November 2013, the Organization for the Prohibition of Chemical Weapons, or OPCW, selected the FDHS to destroy a portion of Syria's chemical material stockpile. The OPCW determined that destruction would take place at sea, and the system's design allowed for employment of the FDHS aboard the MV Cape Ray, a 650-foot-long U.S. Maritime Administration cargo ship. On the ship, an environmentally secure tent enclosure contains the systems, with several other main components outside of the enclosure in the same area. Each side of the enclosure is ventilated to carbon filters to remove hazards. Air from the operational deck of the ship passes through to additional carbon filtration prior to exiting the ship, free of hazards to people and the environment. The FDHS includes a personnel decontamination station, chemical material containers, reagent tanks, holding and pH adjustment tanks, a network of pumps, valves, and hoses, and an air filtration system. The core of the FDHS includes an agent storage tank, mixing vessel, static mixer manifold, and agent, water, and recirculation pumps. The FDHS uses hydrolysis to destroy chemical material. Hydrolysis is the chemical breakdown of a compound due to reaction with water. The term can be broken down from the Greek hydro, meaning water, and lysis, Greek origin for loosening or dissolution, from the word lion. To destroy mustard agent, also known as HD, hot water is first fed into the FDHS large mixing vessel. Then, the mustard agent is fed into the mixing vessel, and the two are mixed vigorously. Hydrolysis of HD removes reactive chlorine atoms, resulting in a waste effluent containing thiodicglycol, a chemical used in ink, and hydrochloric acid, a chemical often used to clean concrete or remove rust. This process is irreversible. HD cannot be recreated from the effluent. The effluent is neither explosive nor flammable. Next, the effluent is pH adjusted with sodium hydroxide, a caustic or base, which neutralizes the hydrochloric acid. The end product is an industrial waste solution of water, thiodicglycol, and sodium chloride, which is a common salt. To destroy DF, which is a precursor chemical for the nerve agent sarin, room temperature water is first added to the FDHS static mixer manifold. Then, the DF is added and mixed directly with the water. A two-step reaction occurs, which removes reactive fluorine atoms. The resulting effluent is an industrial waste solution of methylphosphonic acid and hydrogen fluoride. This process is irreversible, and the effluent is neither explosive nor flammable. The effluent is then pH adjusted with sodium hydroxide to form a solution of water, the salt methylphosphonate, and sodium fluoride. All effluent will be stored on the ship in isotainers, large containers developed to meet specifications for hazardous materials transportation under U.S. Department of Transportation and International Maritime Dangerous Goods Standards. The effluent will be shipped in the isotainers to a commercial treatment facility selected by the OPCW for additional treatment and disposal.